Well, it's 10 o'clock on Thursday, so that brings us to the next edition of the Long Coffee Break. My name's James Murphy. I'm a senior sales engineer here at Long. Today, we're lucky enough to be joined with Steve from Tecogen. We're going to be discussing how to reduce your carbon footprint by utilizing gas-driven chillers. So I'm going to pass it over to Steve, and he's going to take over from here.
Great. Thanks, James. It's great to talk to everyone this morning. A lot to cover, so we're going to move pretty quick, but I'm Steve from Tecogen, and today we're going to talk about combined heat and power systems, mainly a specific form of combined heat and power that Tecogen manufactures called Tecochill, which is a natural gas engine-driven chiller with free waste heat recovery. So a lot of benefits, as you can see there. Just a quick background, we've been in business for about 40 years now. Pretty big presence across the country. Those are all our service centers where we offer factory service. And been doing this a long time. Really our specialty is natural gas engine-driven equipment, from heat pumps, chillers, traditional cogeneration systems, refrigeration units, and so on. So most people on the call, I assume, are probably familiar with what I would call traditional combined heat and power, or traditional cogeneration. Terms are synonymous. So the equipment at the top there, those are traditional cogeneration units that we make. And you're going to put in natural gas into the machine. It's going to turn an engine, then in turn turns a generator. You're going to make electricity and then recover free hot water. So that's kind of the normal way to go about it. That, you know, there's other people that do that out there. We have some unique benefits, of course, but really what makes us unique, and what we're going to talk about for the next 12 minutes or so, is this idea of taking that concept and doing it mechanically. So applying that process to a chiller, where we take the natural gas engine, we connect it directly to the refrigeration compressor. The two shafts are literally coupled together. So that engine is consuming natural gas. It's producing shaft work that's turning a process, in this case, the vapor compression cycle, to make chill water. And then we're going to recover all the waste heat from that prime mover, from that engine, from the exhaust gases, the engine jacket, the engine oil, and deliver that to the customer for free for things like reheat, domestic hot water generation, process heat, what have you. And that heat is all a free byproduct of that process. It's not condenser heat. We're not raising the condensing temperature to try to get useful heat. So it's a little bit different than a heat recovery electric chiller. So just a quick example. I'm not going to focus too much on this, but these are some sites that we have with traditional cogeneration systems. You can see we kind of take this modular approach for redundancy, better reliability. And then again, we're going to focus on the chiller product that we make. So very similar to an electric motor-driven chiller, minus there's no electric motor, there's a natural gas engine. So it's not an absorption cycle. It's not an absorption chiller. That's very important. It's a traditional vapor compression chiller. So it's going to look pretty familiar to you. And it's familiar to a lot of technicians and so on. It's not, it's definitely not an absorber. I want to stress that because we run into that a little bit. But our COPs are about 2.5 times higher than a gas-fired absorption chiller. So, I mean, today you don't hear too much about direct gas-fired absorbers, probably in your travels, but they're still out there. But most of the gas chillers that are sold today are engine-driven, because they're of such higher efficiency and more familiarity from a service standpoint. So we basically make two models, as you can see here. We have a single engine model, just single engine, single screw on the left. And then on the right, we have it's about twice the size, and that's a dual engine, dual screw machine. So those kind of simple two options. If you have a smaller project where you're, say, 600 tons or below, typically the smaller STX series is your building block. And then larger projects, we would use the DTX series as a building block. What's really interesting is that this is a VFD screw chiller. We've had a VFD screw chiller for 30 years. So the engine is the VFD. It's just a mechanical VFD. We have essentially the gas pedal, right? So when we want to change load, we're just adjusting engine speed, in turn adjusting compressor speed. It's the most efficient way to control load and load follow. The smaller chiller does have a hot gas bypass function, really only needed below 25% load. The larger chiller, we turn down to 10% without any hot gas bypass. It's all done with engine speed control. And obviously we turn off one engine on the larger machine. Now we're down to 50% load. So really important. So we have really good turn down and really high efficiency as we turn down. If you look at our part load curve, our efficiency is going up essentially almost the whole way down in load, which is the case for most VFD screw machines. And it is an industrial screw compressor, as you can probably see there. Normally there's an acoustic enclosure over the engine and compressor, but it's kind of removed for clarity. But that's an industrial screw compressor like you would see in an industrial refrigeration plant. So very robust. We do a lot of process cooling with this machine. Anything from making ice at ice rinks. We've been doing a lot of cannabis cultivation work. We're running, in the mid 30s for chill glycol off the cases. We do a lot of hospital work as well with these chillers. They are very efficient from a refrigeration cycle standpoint, flooded evaporator. So, I mean, it's a really efficient machine. So some of the reasons why someone would want to put one of these units in. Number one, natural gas is very inexpensive in relation to electricity. Pretty much wherever you go in the country, you got I'd say at least a 4-to-1 ratio between natural gas and electric costs. So operating cost reduction is a big driver for owners. A lot of places that demand charge becomes a big part of your bill, your time of use charge, essentially completely wiping that off the table here. Oftentimes you run into electric capacity constraint issues. That comes up a lot in cannabis cultivation, but historically over our 30 years, it's come up a lot in hospitals. Hospital goes to expand. They're faced with a $2 million electric service upgrade. We can solve that problem for a lot lower cost and give them all these other benefits. And again, our heat recovery is really high grade heat. It's over 200 degrees. You can do a lot with it. You can reheat. We do pasteurization and process cooling applications. I mean, you can do anything with that heat. It's really high temperature. And again, it's a free byproduct. That's really kind of the most important thing is when you're comparing it to a heat recovery electric chiller, you're not incurring a compressor work penalty to get that heat. It's free. And as far as the power input to this machine, 2.7 kilowatts of single phase power. So very, very small power requirements. It's really just control power, battery charging, and that sort of thing. So again, low temperature is not a problem. Positive displacement compressor, industrial grade compressor. We do a lot of process cooling as well as comfort cooling. Low gas pressure, 4 inches of water column. Pretty much anywhere you have gas needed from the pipeline, you can at least be able to get 4 inches. I mean, it's a quarter of a PSI. So no gas boosters or anything like that. Footprint, very similar to electric chiller. As you can see, the vessels pretty much define the footprint. It can be broken down, just like most electric versions of this, into pieces if needed to rig in. Resiliency is a kind of a big benefit that we hear people talking about a lot with this product today. When a hospital goes to back up their cooling plant, which they may want to do these days, people are backing up a lot more than just life safety in 2020. So what we see is people saying, wow, I can really save a lot in my backup generation if I just put my chiller directly on gas. So that's another big benefit. Here's a quick overview of what it looks like installed. Most of the connections are pretty familiar, cooling tower, evaporator connections, but we have 2 extra sets of connections in yellow, as you can see there. So these 2 that come up from the middle of the machine, those are your heat recovery. Those are going to tie into your heating hot water loop. So whenever the customer can use that heat, that's the first place we're going to send it. And then through a series of thermostatic valves, if it starts to come back to the machine too warm, meaning they're not using it, we typically automatically will reject it to the cooling tower through this dump heat exchanger and these other connections. That's 99% of the case. We would use the cooling tower to do our sort of trimming. We can do a separate radiator if needed. Sometimes when we retrofit to existing tower, we've done that. But typically you're going to use the tower as your engine's radiator, and your heat recovery use is going to be somewhat variable throughout the day. You don't know how those loads are going to coincide perfectly. So you want to have a means to keep the engine at the right temperature, and because your primary goal is to maintain the chill water set point. So really clean emissions when it comes to criteria pollutants. So things like CO and NOx, very, very clean. Actually, pretty much equal to a fuel cell, which is really hard to do with an engine. So we're pretty proud of that. We can get air permitting in pretty much any place in the country, including Southern California. So not an issue. So when we talk about those emissions, just to be clear, those are criteria emissions, not CO2 emissions. We're going to have a major reduction in CO2 emissions as well. And that's just due to the CHP process, which I have a slide a little bit later on that. But again, these are the major benefits. You're reducing your utility costs, your energy costs. You give the owner diversification, their energy needs. So this concept of hybrid chiller plants, we do that a lot, where we have some electric chillers, some gas chillers in a plant. Really lets the owners kind of play the rate structure. Maybe they're going to run the gas chiller, during the day, during peak demand, run the electric units at night. Maybe run the gas chiller to sync up with their heat recovery needs, and let the electric chillers do the rest. If you really want to optimize GHG emissions. So this is that concept again. So this is a really common approach. I mean, in certain applications where there's a lot of waste heat recovery need, it does make sense to just put in all Tecochill units. And there's plenty of places like that. But normally in maybe a hospital or a place where your heat recovery needs are a little bit smaller, really can get a lot of benefit by having both, right? And then for an owner, we're not asking necessarily for people to put all their eggs in one basket. So they want diversity of technology, they want diversity of energy sources. There can be first cost savings by leveraging an electric machine for an N+1 redundant chiller. Again, if you're not going to run the chiller very much, its operating cost implications are moot. So this is kind of a rough example of just how the math works out. So you can see about a 50% reduction in operating costs is very common over an electric chiller. Using the waste heat does get you a little bit of bump lower, but even when you don't, generally just the difference in fuel costs is going to get you savings. And a big chunk of that savings is usually demand. And then when it comes to the GHG emissions, you're going to get a minor bump if you don't use the heat recovery. That's because the grid, is about 35% efficient generation of power at the central plant, 5% T&D losses. So we're kind of almost neck and neck with the grid if we don't recover the heat, right? But the moment you recover the heat, we're taking our process efficiency from 30%, which is the engine's efficiency, and we're raising that process up to 80%. Because we've recovered all that waste heat from that engine, which is something the power plant cannot do feasibly. It's rejecting all its waste heat. There's no way to use it. So that difference between 80% efficiency of our CHP system or our chiller and 30% of the electric chiller from the power plant, that's where you get that huge reduction in GHG emissions. And we can do a whole analysis to show this, but really what you have to do is look locationally too. What is my energy mix? What is the fuel mix at the power plant and this location? It's very different in Colorado versus Ohio versus Massachusetts. The grid is varying degrees of cleanliness and what fuels are in there. So if you have really carbon intense fuels like coal and things like that into the mix, this could look even better than what's shown here. So there's a lot of talk about electrification, which can have some benefits. And I think what people are starting to do too is they're looking at where the power is coming from. How is it being made? When is it beneficial to electrify and when is it not? So I have a couple of quick slides on controlled ag. We've done a lot of controlled environment agricultural work in the last several years. Majority of it has been cannabis, but we have done several leafy greens projects, cucumber project. And it just seems to be a really good fit. The lower chill water cost is obviously a huge benefit to people. Almost every project has some kind of electric capacity constraint that an owner is dealing with in these buildings that they're trying to convert. So we've been able to really help solve those electric capacity problems and give them a lower cost source of chill water. The heat recovery is great. They're using pretty much 100% of it for reheat to dehumidify these grow rooms. Some people are even trying to apply our CO2 from our exhaust into the grow space to enrich the environment. In fact, Project Long was involved in Colorado. They did just that. So we've done many projects so far in the space. I think about 30, getting about close to double that on the drawing board right now, but we've sold about 1,200 tons into this space, which is fairly significant, and really proved ourselves in this market. And so kind of become almost a mainstream solution in that market. Some examples of the projects here. The one on the right side of the screen is actually in Colorado, a project called Ironton. Then another nice thing that we have to offer, and this is in conjunction with Daikin, is a modular chiller plant where we'll put our chillers in this plant with boilers, pumps, and everything, drop it down for the customer. And really nice. One thing that came up in this particular project, this is a cannabis facility. This could be obviously applied to any project, but this cannabis facility was working with a third-party financing company. So the third-party financer actually owns and operates this plant for the owner and sells them energy at a discount. So for this third-party financier, they really like the fact that this thing can be picked up and moved. If things go sideways, they can move it to another deal that they have. There's a lot of risk in cannabis for financiers, so that was kind of an important feature, to not have their system totally tied into the building. So the last several slides are just some examples of our systems in the wild. I believe this is the Escondido City Arts Building in Escondido, California. This is a big hybrid chiller plant with York chillers and some large DTX Tecochills. This is a hospital, same idea, hybrid plant. This is probably a 50-50 split between electric and gas, which is a common way to go. College and the LA area, I believe. And then this is a newer installation of ours at University of Connecticut. We actually replaced 24-year-old Tecochill machines at UConn. So had a good experience with us for 24 years. They decided to put our newer R134A machines in, 1,600 ton plant with 4 units. This is part of a hybrid chiller plant at their central plant. So there's another component here that's electric chillers. This is at, I believe, Kohler Sinks and their main manufacturing facility in Reynosa, Mexico. And an example of an ice rink. This ice rink has 3 sheets of ice, 5 of our single engine screw machines doing all the ice making and as well as air conditioning. You can just see on the right, all the places we're sticking this waste heat in this facility. We're pretty much doing everything with our waste heat in this facility. They're almost using no gas otherwise. So yeah, that's the quick overview. Hopefully that was interesting to you folks, and maybe we can do some individual webinars, some of the firms, James.
Hey, thank you. Thanks. Join us next week. Jason Long will be leading the coffee break, and he will be discussing data-driven air quality with Atmos Air. So thanks, and have a great day.